Okay, this is the Chapter 7 quiz. Number 1, following a recent dramatic drop of 500 points in the Dow Jones Industrial Average, a poll conducted for the Associated Press found that 92% of those polled said that a year from now, their family financial situation will be as good as it is today or better. Which of the following terms describes the number 92%? So we need to find 92%. It's of those polled, so it's from a sample. And since that number is from a sample, we're going to say it's a statistic. So remember that sample goes with statistic and parameter goes with population. Number 2, what is distribution? I guess they want what is the distribution of values taken by a statistic and all possible samples of the same size from the same population called. That one's going to be D. It's the sampling distribution of the statistic. It's just the definition of what a sampling distribution of a statistic is. So there's not really anything to explain there. Just know the definition of what a sampling distribution is. Okay, number 3, if a statistic used to estimate a parameter is such that the mean of its sampling distribution is equal to the true value of the parameter being estimated, what is the statistic said to be? It's what we want it to be. It's unbiased. And again, it's just kind of the definition. We just keep saying we want an unbiased estimator. In order to do our sampling distribution, we want the statistic to be an unbiased estimator. Okay, number 4, suppose you take a random sample of size 25 from a population with a mean of 120 and a standard deviation of 15. Your sample has a mean of 115 and a standard deviation of 13.8. Which of the following has a mean of 120 and a standard deviation of 3? It's going to be the sampling distribution of the sample mean that's going to follow the rules that we have on the formula sheet. The rules on the formula sheet are mu of x bar is equal to mu, and then the standard deviation of x bar, and that's really saying it's the x bar thing that I'm writing. It's the mean of the sampling distribution. It's not just one single sample. Okay, so the rule again from the formula sheet is the standard deviation divided by the square root of n. So your individual sample is really useless information. We don't need it at all. And so we know that the mean of our sampling distribution is going to be the same as the mean of our population, which makes it 120, which is what they say here. And then the standard deviation, we need to know where that 3 came from. So they took the population mean, which was the population standard deviation, which was 15, given here, and divided it by the square root of our sample size. Our sample size was 25. Okay, so we're going to do the square root of 25. And so you can use your calculator for that. 15 divided by the square root of 25, that's just 15 over 5. So that's where they got the 3 from. And so that makes it answer choice C. It follows the rules on our formula sheet for the sampling distribution of means, of sample means. So that's going to be C. Number 5, in order to use the formula, standard deviation of our sampling means is equal to the standard deviation of the population. Standard deviation of the population divided by the square root of n. To calculate the standard deviation of the sampling distribution of the sample mean, which of the following conditions must be met? So we need 1 and 2 to be true in order to do z-scores, in order to do normal CDFs. In order to do z-scores, in order to do normal CDF, that kind of thing. But we don't need them to be true in order to use the formulas on the formula sheet. The only thing we need to be true is the 10% condition that says the sample size needs to be less than or equal to 1/10 of the population size. Okay, so we only need 3 to be true, so we need C. Again, 1 and 2 are great. We want those to be true so that we can do z-scores in normal CDF, but we don't need them to be true to use the formula given that's from the formula sheet. Okay, number 6. The central limit theorem refers to which of the following characteristic of the sampling distribution of the sampling mean? So the central limit theorem tells us that as long as we have a sample that's greater than 30, then we can assume that the shape of our distribution is normal, which allows us then to do z-scores and normal CDF and all that. So reading each answer choice A is the best answer here. So regardless of the shape of the population, if we knew the shape of the population was normal, we wouldn't even need the CLT, because if the population is normal, then our sampling distribution is also going to be normal. But since we don't know that, so regardless of the shape, the sampling distribution of the sample mean from sufficiently large, and by sufficiently large, they mean 30, okay, samples will be approximately normally distributed. That is the definition of CLT and what it allows us to do. So B, this is talking about the 10% condition, if you're using that formula, so that doesn't work. Again, the mean's going to equal the mean of the population. This one, again, that's the 10% stuff. That doesn't have to be normal for that to be true. As you take large and large samples from, I'm looking at D now, the standard deviation, we don't care about that again, because we just want, the CLT just lets it be normal, the shape be normal, and lets us do normal CDF and Z-scores. So that'll be A. Number 7, a simple random sample of 1,000 Americans found that 62% were satisfied with the service provided by the dealer from which they bought their car. A simple random sample of 1,000 Canadians found that 59% were satisfied with the service provided by the dealer from which they bought their car. The sampling variability associated with these statistics is, and we need to calculate them to see. So we have 1,000 Americans, we have 1,000 Canadians, but they have a different proportion for each. Variability is going to, one of the types of variability, I should say, is standard deviation. So we can assume that 1,000 Americans is probably, most definitely going to be less than or equal to 1/10 of the population of America. And then same thing with 1,000 for Canadians. We're going to assume that that sample size is less than or equal to 1/10 of the population of Canada. So we can use the formulas given to us on the formula sheet. We have the standard deviation of P hat, so the sampling distribution of all proportions is going to be equal to the square root of P times 1 minus P over N. And so you're going to plug in the value separately for the Americans, and then you're going to plug it in separately for Canadians. And I've typed that in the calculator. And so you end up with, for the Americans, you're going to do square root of 0.62 times 1 minus 0.62 over 1,000, because it said for both of them our sample size is 1,000, and you get 0.0153. And then for the Canadians, you change your proportion, so you want to do the square root of 0.59 times 1 minus 0.59, still over 1,000, because they also had 1,000 in their sample, and you get 0.0156. And so they're very, very close together, but they're not exactly the same. So that's going to be answer choice B. So you definitely need to calculate them to see that they're very, very close, but not the same. Number 8, a student investigating study habits asks a simple random sample of 16 students at her large high school. So they're pointing out that it's large. So we're going to assume by large that, her high school's over 160. So we can use the formula on the formula sheet, because we have to have 16 be less than or equal to 1/10 of her high school. So since it's large, we're going to assume they have more than 160 students. How many minutes they spent on their English homework the previous night? Suppose the actual parameter values for this variable are mu is 45 and sigma is 15. So we have a mean of 45 for our population, and we have a standard deviation of 15 for our population. Which of the following best describes what we know about the sampling distribution of means for the student's sample? And so we do know from our formula sheet that the mean of the sampling distribution of means is going to be equal to just the mean of the population. So that is going to make it 45, which I know is not very helpful because all the answer choices have it to be 45. So then we move on to the standard deviation. And from the formula sheet, the standard deviation of the sampling distributions of sample means is going to be the standard deviation from the population divided by the square root of n. Okay, so standard deviation from the population was 15, and it said that her sample was 16 students. So we want to divide the 15 by the square root of 16. So 15 over 4 gives you 3.75. Okay, so you type in your calculator, you get 3.75. So that leads us to either picking D or E. So we need to know, do we think that this distribution originally is normal, or excuse me, we want to know if the sampling distribution is approximately normal, or do we not have a way to tell what the shape of the distribution is? And so we have two ways for the sampling distribution to be approximately normal. The first way is if they told us the population was normal, and they didn't do that. So we cannot assume that the original population was normal. And then the other way is the central limit theorem, which tells us if our sample size is at least 30. So if n is greater than or equal to 30, then we can say that we do have an approximately normal distribution, but n is equal to 16, so this does not work for us either. So we're going to go with E. We don't know the shape of the distribution because our sample size is not big enough, and we don't know that the population originally was normal to begin with. So it's unknown shape. Okay, number 9, olive weights. Olive weights are classified according to a unique set of adjectives implying great size. For example, the mean weight of olives classified as colossal is 7.7 grams. Suppose a particular company's crop of colossal olives is approximately normally distributed with a mean of 7.7 grams and a standard deviation of 0.2 grams. Which of the following represents the probability that the mean weight of a random sample of 3 olives from this population is greater than 8 grams? So we just want to know the setup of a z-score, and you might ask yourself at first, like, can we even do a z-score? Are we allowed to do that? But since the original population was said to be approximately normal, we can do normal CDF. We can do z-scores. So since all of our answer choices are already set up as z-scores, we're not going to be able to do the normal CDF. We're going to have to know how to set up a z-score. So the z-score is set up as the observed score minus the mean divided by the standard deviation. Okay, and in this problem, we're talking about means. Okay, so we're not going to do the proportion formula, obviously, from our formula sheet. We're going to do the mean formula. So we're going to do observation minus mean over standard deviation, but our standard deviation is going to be the population standard deviation divided by the square root of n. Okay, so whatever they want it to be, they said greater than 8, that's our observed score. But I'm going to focus for a second on the greater than. If I want it to be greater than 8, then I want my inequality sign to be greater than. So that allows me to eliminate C and E right off the bat because those both say less than. Okay, A, B, and D all say greater than. So that's important. And then I also can eliminate D right now because I know the standard deviation on the bottom is not set up correctly. Okay, they're setting that up. That looks like square root of P times 1 minus P over N. That's for proportions. We don't do that when we're talking about means, so it wouldn't be D either. So A and B both have the standard deviation set up correctly. We have the standard deviation from the population, 0.2, divided by the square root of 3, which is the square root of our sample size. So that's good. So picking between A and B, I just need to pick the one that has the observation minus the mean, not the other way around. Okay, so the one that's set up correctly is A. You have your observation minus your mean over your standard deviation, where the standard deviation is the population standard deviation divided by square root of the sample size. So that's got to be A. Okay, on number 10, in a large population, 46% of the households own DVD recorders. A simple random sample of 100 households from this population is to be contacted and the sample proportion computed. Which of the following expressions represents the probability that more than half the household sampled will own a DVD recorder? So I want to go with more than half. That's important to us, more than half. So we want to be greater than. So that does allow me to get rid of right away the B. That doesn't work. And then is that it? Okay, so the other 4 are all greater than. So it wasn't that helpful, but hey, at least we're picking between 4 now. But I also want to point out that we're dealing with a proportion this time. We're not dealing with means this time. So the proportion formula for standard deviation, so for it's the standard deviation of the sampling distribution of proportions, is going to be the square root of P times 1 minus P over N. And again, you can look on the formula sheet and that is there for you. So that P that we're looking for in the problem is going to be the population proportion. So that was given to us as 46%. And so we want to do 46% times 1 minus 46%. which is going to end up being 54% if you actually do that subtraction. And then divided by our sample size, they said they did 100 households. It's going to be divided by 100. So you're looking for that to be on the bottom of your z-score. Remember, we're looking for observation minus mean over standard deviation. So when I look at just the standard deviation alone, B and E look like they're set up correctly. A does not work for me, and then C does not work for me. So we're looking and choosing between D and E. And so at this point, all we're looking at is, did they put the top in order correctly? Observation minus mean. So we're doing more than half. So our observation needs to be the half, and then the mean of the population. Remember that on our formula sheet, it says the mean of your proportions of, or the center of your proportions, your sampling distribution of proportions is equal to just the center or just the proportion of the population itself. And so that's going to be that 0.46. Okay, so our formula on the formula sheet allows us to just use that as the mean. But the observed score comes from them saying the half. Half comes from, or gives us the 0.5. So E is the correct answer here. Okay, on to the short answer tree. Response number 11. A study of college freshmen study habits found that the time and hours that freshmen study each week follows a distribution with a mean of 7.2 hours and a standard deviation of 5.3 hours. Can you calculate the probability that a randomly chosen freshman studies more than 9 hours? If so, do it. If not, explain why not. So we don't know the shape of this distribution, and there's two reasons we don't know the shape. I'm just going to say no, we do not know the shape of the distribution and be done with it, and then I'll explain it. Okay, so we don't know the shape of the distribution for two different reasons. For one thing, they didn't tell us that the original population was normal. Can't do it for that reason. And then also, we don't even know what the sample size is. We just have a study of the college freshmen, blah, 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 but they never tell us how big our sample is. So if our sample was 30 or more, then we could do a normal CDF and we could figure out the probability. But since they didn't tell us how many people are in or how many freshmen are in our sample, then we can't do it because we don't know the shape of the distribution. We have to prove it's approximately normal before we could do z-scores or normal CDF or any of that. Okay, part B, what is the shape of the sampling distribution of the mean X bar for samples of 55 randomly selected freshmen? So we're going to say it's approximately normal now, and I feel comfortable saying that because now we have our sample size. Okay, so we're at it's approximately normal. Okay, so back to why is that true? Because it does say that we have to justify our answer. So we would say since n is equal to 55, that is greater than 30, so the CLT applies. You don't have to write out central limit theorem, but we do need to at least abbreviate and say what we're using to say that it's approximately normal. So it is approximately normal by the CLT, because as long as our sample size is greater than 30, then we can say that our sampling distribution is approximately normal. Okay. Part C, what are the mean and standard deviation of the sampling distribution of the mean X bar for samples of 55 randomly selected freshmen? So we're going to use our formula from the formula sheet. We have the mean of the sampling distribution of all the sampling means. It's going to just be equal to the population mean. And so we get to say it's just 7.2. But the standard deviation, we do have to work out a little bit. So we're going to use the formula from our formula sheet that tells us to take the population standard deviation and divide it by the square root of the sample size. So the population standard deviation given to us is 5.3. The sample size given to us is 55, so we want to take the 55.3 and divide it by the square root of 55, and then the calculator gives us the answer of 0.7147 when we round that. Okay, part D, find the probability that the average number of hours spent studying by an SRS of 55 students is greater than 9 hours. Show your work. For me, it's going to be enough if you just show me what you typed in the calculator, if you don't want to do the z-scores and all that. So we are allowed to use normal CDF because remember, we did assume it's approximately normal. Since we do have a sample size of 55, that is enough. It is greater than 30. We're going to have a lower bound of 9 because it says we're greater than 9 hours. We're going to have an upper bound of positive infinity. I'm just going to let it be 1,000. I'm going to use the mean from part C, which was 7.2. I'm going to use the standard deviation from part C, which was 0.7147. Okay, and really that's the mean of X bar and the standard deviation of X bar if you want to get really technical about it. So I typed all of that in my calculator, and I got the answer from my calculator 0.0059 when you round it. And so that's about 0.59% of the time. So it's not even 1%, it's 0.59% would be the probability of that happening. Okay, number 12. A freshman is offered to play a game with you that involves flipping a coin that he has provided. Since a flip of heads will be to his advantage, you want to test the coin for fairness before you begin to play. Your friend is willing to let you flip the coin 50 times to determine if the probability of getting heads is actually 0.5, as it should be if the coin is fair. Part A, assume for the moment that the coin is fair. If P hat is the proportion of heads and 50 flips of the coin, then what are the mean and the standard deviation of the sampling distribution of P hat? So according to our formula sheet, and we can do this, it doesn't really tell us to explain it until we get to B. But anyway, why are we allowed to use these formulas? It's because you can flip a coin infinite number of times. So of course, if you're flipping it 50 flips, then yes, that meets the 10% condition, because of course 50% is less than or equal to 10% of infinity. So that's kind of just a given that we can do it. So the mean of our sampling distribution of proportions is going to be equal to just the population proportion, which is 0.5. Like you would know that you're going to get heads on, you know, in the long run, on average, if you do it over and over and over, you're going to get really, really close to 0.5. That is the proportion of heads you would expect to get. Again, from the formula sheet, we're going to do the square root of P times 1 minus P over N. So the P is 0.5, 50% heads, and then 1 minus P is going to just be 1 minus 0.5, and it said he's flipping it 50 times, so it's a sample size of 50. I did use my calculator to calculate that for me. Don't forget that alpha trace will let you get your fraction button. That's always very helpful to not have to worry about all the parentheses and all that fun stuff. So rounding that, I would get 0.0707 for the standard deviation. Okay. It says explain why you can use the formula for the standard deviation of P hat in this setting. So again, the population of possible coin flips is infinite. And so we don't even need to worry about the sample size. So I'm just going to say, so, you know, the 10% condition is met. And that 10% condition says that n has to be less than or equal to a tenth of n. But if this is infinity, then of course, you know, 50 is plenty, you know, it's not too big or whatever. So yeah, of course, that's fine. Okay, part C, you flip the coin 50 times and you get 30 heads. Do you risk insulting your friend by refusing to play with his coin? Support your answer with an appropriate probability calculation. So the first thing I wanted to look at was what percentage of times did they get heads? So 30 out of 50 would be 60% because 3/5 is 0.6. Okay, so 60% of the time they did get heads. And so we want to find the probability that your proportion is greater than or equal to what you got. So we got or it doesn't matter, equal to is fine, greater than or equal to the 0.6. So in order to find that probability, I did normal CDF. I'm going to write it out because I didn't actually mean for the calculator to pop up yet, but that's okay. So I did normal CDF. I want to go greater than or equal to 0.6. So my lower bound's going to be 0.6. My upper bound's going to be infinity. So I just did 1,000 there. The probability of really getting ahead, you know, the true proportion of heads is 0.5. And we answered that in part A. And then the standard deviation, when you had the 50 flips, was 0.0707. And again, that was from part A. Okay, so as you can see, when I type all that in the calculator, I get 0.0786. And so I would say 7.86% of the time, that's going to happen. So we're going to use part C's answer. Oh, actually, it's right here. It says, do you risk insulting your friends? We're not actually done answering this yet. So remember, I told you guys that if it's lower than 5%, then we call your friend a liar. We're like, no, you have like a weighted coin or something, like you're lying. This is not a fair coin. But if it's over 5%, then we'd say, yeah, this could happen by chance. It's not super likely to happen, but 7.86% of the time, like that's enough of it that it could just happen by chance. So it says, do you risk insulting your friend by refusing to play? So don't risk it. We want to say, do not risk it. Don't insult your friend. Don't call him a liar, all that good stuff. Okay. 7.86% is high enough. Excuse me, probability. That 30 out of 50 could just happen by chance. Okay, so again, if we had a percentage that was lower than 5%, then I'd say yes, risk it, call your friend out. You know, if we had like 4.5%, we'd say 4.5% is such a low probability that probably couldn't happen by chance. So we would change our answer if it was below 5%. But since it's above 5%, we do say that that's a high enough probability that, you know, it could have just happened by chance. Guys, number 13, probably not going to see anything like this on your chapter test. So you're going to see I just kind of gloss over this because it's really not the way it's going to be presented. So it's just kind of a weird question. We haven't had anything like it even on our daily check. So, but let's just take a look at it really quick. Teenagers send many text messages. Recent polls cite medians of more than 50 per day. Consider a large population of teenagers for whom the distribution of the number of text messages sent per day is strongly skewed to the right. Here is the 5-number summary for number of texts per day for this population. We have a minimum of 0, the first quartile is 20, median is 55, third quartile is 140, maximum is 250. Suppose we take random samples of size 32 from this population and we calculate Q1. So they're just calculating the first quartile for each of our samples. Below is a dot plot of Q1 from 50 such samples. Briefly explain what the dot at 35 represents. So it's like one of the samples of 50 that they took, just one of them had a first quartile of 35. That's what that represents. So it says the dot at 35 represents the first quartile of just one of the 50 samples taken from this population. So if I counted the dots on this picture right here, there should be 50 of them. And so each of those dots represents the first quartile of one of the different samples that they took that were of size. Or they have size 32, I'm sorry, they were size 32, but they took 50 of them. And so that was just one of those 50 dots. And then part B, is the sample Q1 an unbiased estimator of the population Q1? Justify your answer. We know the 5-number summary that the true population value, or from the 5-number summary, that the true population value is 20. So they gave us that Q1 is 20. And if you look at the center of our data, if you actually go and count the dots and find the 25th point, it's going to be in there. So it's about 22. It's higher than 20. So we would actually say it's a biased estimator because it's a little bit too high. The center of this data that we see is actually at 22. And so we would say, no, it's not an unbiased estimator. It's actually a biased estimator for the population. So that's it. Make sure you're studying for your test. Chapter 7 test for you guys will be on Tuesday when we get back after Thanksgiving. So let's see, what date is that? The 27th? Nope, sorry, 28th. So when we return on Tuesday the 28th, then we will have the Chapter 7 test. I will be at school on Monday the 27th. So if you have any questions, you can come by before school, after school, and ask any questions, have tutoring, whatever you need to get ready for the test on Tuesday. I'm so sorry that it did fall right after the holiday. We talked at length about trying to move it around and we just couldn't figure it out, guys. So just come see me on Monday if you have any questions about anything. Have a good break. Be safe.